Started? Okay. Good morning, people. Today's class is rather a marathon class. It's 1 hour continuous talk, and I've got my water bottle ready so that in case I need more water in between. Today's class is on consolidation. In fact, if you're new to this subject, this topic, I suggest you get a paper and pencil ready because there are few terms we would come across in today's class which are pretty handy, pretty important for us to understand. So on this we will speak about, today's class we'll speak about compressibility, we'll speak about Terzaghi's model, as well as the third point, which is on consolidation settlement. So we look at these three aspects, and if given a chance, we'll also look at the pore pressure dissipation, which is based on Terzaghi's model. Incidentally, the cartoon on the right, I have zapped it from a conference proceeding in which it's a very funny cartoon. It shows how consolidation settlement can be so severe. It shows that at the time of construction of Leaning Tower of Pisa, there are two architects. They are discussing, they're doing a discussion, and it's very small, written quite small. I'll just read it out. It's one of the person is trying to tell the other that I saved a little on the foundation, but no one will ever know. Okay, so that is history, and in fact it also speaks about how dumb the architects are. We engineers are super. Okay, so come back to our today's topic. We say that the soils deform when loaded. This is true. When you load a soil, they will deform. They have to deform, irrespective of what the load magnitude is. And this deformation can be manifested as either the change in shape, which will cause distortion to the soil or the material, or the change in volume. So change in volume is the second aspect, which will be which will also result in deformation. To give you an example of change in volume, if you take a lump of soil and squeeze it with equal pressure from all around, we call it as an isotropic loading, meaning equal. That will result in pure volumetric changes. A change in shape would be if you keep the volume constant and then try to distort the material. That would be pure shear distortion. So over here we have an example of a structure. In fact, this was meant to be an animation, but unfortunately on PPT this animation died out. What it tries to show is a structure which falls, collapses based on ground settlement. So what are these settlements we are looking at? I've got an expression at the bottom. If it's not clear, do not worry. It simply shows the total settlement should be equal to the immediate settlement. Total settlement should be equal to the immediate settlement. The immediate settlement is the elastic settlement, meaning you can recover. This is recoverable. You can recover elastic settlement. The second one is the consolidation settlement, which will result in the above two. That means the change in shape or the change in volume or a combination of both. Most likely it results in combination of both. The third one is the secondary consolidation, which is because of a settlement at constant volume. Now we will not touch on this aspect because it mainly deals with soils which are organic in nature. So secondary consolidation or creep phenomena, I would say, is not part of our syllabus today. We will mainly concentrate on the second one, which is the consolidation settlement. So as an engineer, we have two questions to answer. That's the two important questions. Firstly, how much settlement will occur? Okay, and second, how fast it will occur? Okay, so this today's lecture is based on these two, how to answer these two questions. So I have a question for you right now. The question is, what happens when you load a soil? When you load a soil, load ground. I have three options, and you've got to choose the best of the three. The soil grains will deform, or the air and water in the voids will compress, or water will squeeze out of the voids. Remember, in this entire chapter, we only deal with saturated soil. Consolidation will only occur, or we will only observe consolidation in saturated soil. That is the bottom line. You can't defy this rule. So out of these three, if you have looked at these 3 points carefully, soil will never ever deform. Under most of the building loads, any kind of load from the superstructure, soils are never deformed unless you're dealing with calcareous deposits. Calcareous deposits are made of seashells. Those kind of soil particles are different class of material, calcareous deposits. So even under the Burj Khalifa at Dubai, we won't say the soil grains will deform because soil grains have high rigidity. The second thing, air and water in the voids, they too will not compress because like soil grains, the air is out. Of course, air is out. Water, similar to soil grains, water also has high rigidity. Although not as significant high as soil grains, but still significantly high for our normal engineering loads. It leads to the third option, which is water will squeeze out of the voids, and we will look at this very carefully in this lecture. So when water squeezes out, the grains will rearrange into stable. I put denser in quotes because normally we use dense for a granular material, but I've generalized this word denser because the particles will come closer. When water squeezes out and with under the superimposed load, particles will come closer. We take an example of compressibility of granular soils. So take an example of sand and what happens to sands when they're subjected to load. In this case, I have a plot of void ratio versus effective stress. Effective stress meaning what is the magnitude of load you apply post every excess post long-term behavior. I will come to this excess pore pressure in a while, but this is the assume that this is the magnitude of load you have applied on the horizontal axis. Vertical axis is the void ratio, so you're looking at change in void ratio. The two plots, one which is of dense sand and the other loose sand, show quite a significant change in the void ratio upon loading. In the increase in effective stress, there is a decrease in void ratio. In other words, there would be the both, irrespective of loose or dense sand, the material gets compressible. It compresses. It is noted that loose sand shows greater change in void ratio compared to the dense sand. Obviously, loose sands have more voids, so I would say the void ratio being greater would mean that loose sand is loosely packed, so it will settle more. If I look at the change in void ratio, the complete change, and replot in a scale such that 0% is at the starting or the original void ratio and 100% is the final settlement or the final compression or the maximum change in void ratio which can occur. We will look at this scale later, when you're looking at relationship between the change in void ratio and the change in volume. Okay, so for the time being, just understand that this scale 0 to 100 has been somehow been taken into account the entire change in settlement. So what we see is for sands, the entire settlement, nearly 100% settlement, is over within days. If you're looking at a layer of deposit. In other words, the structure which is imposed on the soil will experience little additional settlement after the construction because most of the settlement is over during the construction process itself. Take an opposite example of clay. Okay, remember we have a plot of void ratio versus the load you have applied, and we have already looked at the sand cases, the loose sand and the dense sand. And if I try to superimpose the clay figure, the results of clay, it's quite obvious that even the clays, with the increase in load, the compression increases, meaning there's a significant change in void ratio. The second thing is the decrease in void ratio, or the change in void ratio, is much larger in clays compared to sands. And if I retake this scale, the change in void ratio, and plug it in terms of change in volume, or the change in compressibility from 0 to 100, what I see is the sand which got 100% settlement or 100% volume change within days. For clays, it takes months or years. That is the significant difference between the two. It's because of the permeability. The clays have low permeability, which controls the rate of, how the compression occurs, or how the rate of dissipation of water occurs. And we will look at this again in detail just to after this introductory remark. So what we have is, in order to explain all this, take an example. We take an example of how Terzaghi went around and explained the same concept to a group of experts. And during Terzaghi's time, whenever if you had a great invention, you would normally go in a seminar and present this. And Terzaghi was in fact, by virtue of training, a mechanical engineer. Although we call him as a father of soil mechanics, but by training he was a mechanical engineer. And any project he developed in favor of soil mechanics, because of his mechanical background, he always had a gadget, a simple gadget to explain the phenomena. We have, in this class, we have borrowed the same gadget which Terzaghi had used to explain, in which there's a cylinder, and at various exits of the cylinder there are standpipes. So standpipes attached to the various exits of the cylinder. In between the cylinder there are number of perforated plates. Each plate is connected to the adjacent plate by springs. What you see is, in between the plates is filled with water. So what Terzaghi tried to explain was, the perforated plates are similar to your voids, the voids of your soil. The springs are similar to your, or akin to your, or they represent the soil particles. The water in the container is the water which fills with the voids, the voids in the soil. So with this model, he went on to explain the phenomena of consolidation to a group of experts. So let's look at what happens in the next slide. So this is the same cylinder in which water is filled up at the top, and by virtue of our previous few lectures, we know, because this container, if it's closed, there is no flow, all the water in the standpipe will rise up to the same level in all the standpipes. Okay. So the second, if you look at the second cartoon over here, the surface is loaded by some kind of pressure or load. Say, let's call it sigma for the time being. And immediately upon loading, what happens? That's what Terzaghi tried to explain. Immediately upon lowering, all the water in the standpipes rose up to a level, and there is no absolute deformation of the spring. Take an example, when I immediately load the container, and if there is no tap, take an example that there is a container and I have a tap. So when I load the container and I close the tap, load the container, what happens? There is no opportunity for the water to escape. In this case, the perforated plates are laid in between. However, assume that there is a tap and it's closed. If it's closed, when I load the whole container, the water does not escape. There is no chance for water to escape. So what happens? The entire load is carried by the water. If I make the statement, the entire load is carried by the water, is it true? Because if there is no escape of water, it means that none of the springs will compress, correct? If the springs do not compress, can I make a statement that the springs will not carry load? by virtue of our physics understanding, springs only carry load when they compress, or upon loading, because of the stiffness of the spring, they will compress. So if I come back to this particular, second cartoon over here, since there is no compression of the spring, I have the tap closed. The springs and do not carry any load. So what happens to the vertical load which is imposed from the surface? This entire load has to be carried by someone, and in this case the water. And water, when it carries the load, it has to result in some kind of display, and this display is the rise in water table in the standpipe. So if I measure the height of water, okay, the height of water, I can correlate this height of water to my water pressure. Remember, I have the unit weight of water known, the height known. So if I play around with these terms, I can equate sigma to the height of water. I suppose this should be very clear because unit weight of water is fixed. So what happens if the water starts to dissipate? So we are looking at this third cartoon over here, meaning I have opened up the tap. If I open up the tap, the water from the topmost plate, perforated plate, will start to move out first. Remember, it's a closed container. Water can't escape from anywhere except from the top. So water will try to escape from the topmost plate. In other words, the springs which are very near the surface, they will start to compress, or they will start to take in some load. Their share of load starts to develop. In other words, the topmost standpipe, the water level in the topmost standpipe will gradually start to lower down. Whereas the water level in the bottommost standpipe, in which the springs have not seen any of the load because there is no compression, the water pressure still remains the same. Okay? What happens if I gradually allow the water to dissipate with time? The springs will start to compress from top to bottom, and gradually you'll see a drop in water level in all the standpipes. This is very, simple explanation of how the water escapes, how the soil grains which are akin to the springs carry the load, and how the dissipation is closer to the surface through which drainage is allowed. Okay? We're going to put all this in words in English in the next slide. But before we do that, let's look at one term which is important on this slide, which is pressure head isochrone. Remember, iso is same, chrone is time. So at same time, what is the pressure head? Meaning if I join a line, if I join all these points, the topmost points, the curve, it would be called as the pressure head isochrone, because each one of these standpipes give the pressure head, and I join the topmost point, it's iso, same, chrone, at the same time, this is the pressure. And with long term, when entire, the springs carry the load, meaning all the springs are compressed, the water has reached its hydrostatic case. In this case, the normal level somewhere here, and what you see is the water level has reached the same point in all. In fact, this level inside the container, I should have covered this with blue. Apologize, this should also be blue, and it should be at the same height as this level, meaning the new hydrostatic level, which possibly, because of the overflow mechanism, possibly will be close to the older hydrostatic value. Okay? So the conclusions from this Terzaghi study, and these are important points because these are related to our soil mechanics. The first one is the pore water pressure is hydrostatic before the application of external load. So prior to the application, the pore water pressure was hydrostatic. Remember the container model. Second, excess pore water pressures were generated upon loading. And these pore pressures generate transient, meaning time-dependent flow condition. Remember, with time, the excess pore pressure gradually dissipated with time. Okay. The third one, consolidation started, meaning the springs started to take load, and the springs started to compress. So consolidation started or progressed while the excess pore water pressure dissipated. Okay. The last one, which is important, dissipation of the excess pore pressure started closer to the drainage boundary. Remember the topmost perforated plate, the drainage occurred from the topmost perforated plate, and gradually the inner plates also started to, the pore water from the inner plates also started to escape, and the plates or the spring compressed. Okay. This leads to, in fact, a better definition of consolidation, and I've zapped the equation or I've zapped the consolidation expression over here. It says consolidation is a decrease in soil volume by squeezing out the pore water because of the gradual dissipation of excess pore water pressure, which was induced by the total load applied over the surface. Okay. Let's take an example of how consolidation is measured, or I would say the properties of consolidation are measured in the laboratory. Please take a look at the top 3 photographs, and you would probably identify one of the equipment in your lab with one of these 3 photographs. A similar equipment would exist in your lab. Please take a look at the photographs. What we see over here is, all the 3 photographs in fact represent the same soil cake. I call it soil cake. This is a soil specimen or the cake. Okay, it's a sketch shown of something which is on top of this frame, somewhere here. Over the soil cake, I have applied load. Okay, please do not worry about these stones, the loading plate, because you're not too much concerned about the equipment today. But what we see is when you apply load to the specimen, the water will squeeze out. Water will start to squeeze out from either here or there. In this case, over here we have a standpipe. Probably, if you open up the valve, the water will squeeze out. And you always keep this, water up to brim, up to the top level, such that, the soil does not dry out. The usual plot of this kind of result is a void ratio versus effective stress. Okay. Effective stress, I have written sigma V over here. Zoom in. I have written sigma V prime. Okay, so I assume that this is effective vertical because I apply vertical load. That's why the suffix V comes in. So if I apply, take a cake of soil and apply the vertical load from the top, so shown by this red arrow. Apply vertical load. I know this soil sample will consolidate or squeeze in, and I allow the nature to do its job. Meaning I wait for the entire squeezing in or the compression or the consolidation to be over. So say for example I come next day and take a reading. Remember, come next day all the excess pore pressures will be dissipated. The next day the pore pressures on this sample would be the height of water level in this on up to the brim, because all the excess pore pressures which go out will dissipate, or with the overflow mechanism if you have an overflow mechanism. And what happens to the effective stress? Remember one of the previous lectures we said total stress equals to effective stress plus the pore water pressure. In this case the pore pressure is just this much, you can neglect it, you can ignore the small height of water or the small pore pressure. In other words, the total stress which you have applied equals the effective stress. If I plot this value on this figure, I should get a point somewhere here after the nature has done its job. Okay, so that's the point over there. So it signifies the void ratio after consolidation and the effective stress value, meaning in this case equal to the total applied load, because the pore pressures are 0. So what happens if next day I come and add another stack of load? I'll get another stack of points. Likewise, I come the day after when the nature has done its job and so on. I'll get a stack of points which show, remember the curve, one of the first curve on this presentation, the compressibility or the change in void ratio with effective stress. Effective stress in this case is the total stress minus the pore pressure, whereas the pore pressure is 0. So it's the same figure. I connect with the points. I'm going to zap this figure on the next slide, please. It's the same figure over here, void ratio versus effective stress. Remember at the beginning of this class I said please get a paper and pencil out. And now is the time to really jot down the first definition or the term which is used in consolidation. So if I have a plot of void ratio versus effective stress, both in the normal scale, I'll get a curve. And if I look at this change in void ratio at between any 2 points, with the change in effective stress, I have a delta E, that's a change in void ratio, and delta sigma P prime, change in effective stress. And if I take this proportion, meaning change in void ratio over change in effective stress. Remember, this is a proportion, it should have a dimension of inverse of stress, because void ratio, the dimension is dimensionless, effective stress value should be, for example, kilonewton per meter square. So this value has inverse of stress. This whole definition by definition is called as coefficient of compressibility or AV. If I look at this figure, I take points anywhere along the curve, AV is bound to change. In fact, you will find that the AV decreases with the increase in effective stress. It is not constant. Okay? Take an example of this figure. You can please go home and look at this figure carefully. As we go down, if I select these 2 points, I have a different void ratio. If I select these 2 points, the change in void ratio is different, although the change in effective stress in both the case is the same. In other words, AV decreases with the increase in effective stress. So we've used the first term, coefficient of compressibility, AV. Oops, sorry, I think I double clicked. No, I single clicked. Apologize. Let me go to the next slide. You'll come across a number of other terms, and I would like you to please concentrate on this in case you are new to this section on consolidation. You'll come across these terms VCL, NCL on the next slide. Let me go to next slide. Before that, there's an important thing for you to remember. Soil will remember, soil tends to remember the maximum load it has been subjected to in its history. I always like to put this in a very easy statement. Soil has a memory of an elephant, meaning if you kick an elephant, today, as a baby, if you kick a baby elephant today, 25 years from now, it will always remember your kick and it's going to kick you back. Okay, that's the same analogy applies to soil. If you load a soil today, it will always remember that load, unless you exceed that load. You exceed that load, then it will remember the new load. Okay, so as long as you are lower than the maximum load, it has been subjected to its history, it will always remember that load. If I keep this in my mind, and if I look at the plot, again, please look at the left curve, void ratio versus effective stress, and I have already seen a plot of A which goes down to B. Please ignore this B to C, okay, for the time being, please ignore this B to C. What I see is this is the same curve which goes down A to B and comes down. Okay, this shows a lot of a curvilinear is a curve. Much of this curve I can reduce if I convert this in log scale. In today's lecture, this is log, log to the base 10. In other words, this first curve, which is which shows over here, is possibly the same curve which is there. From A to B, which is the curve, if I convert to log scale, it becomes it becomes a straight line. Okay. Now let's look at this loop, unload this loop over here. Now, if you have performed consolidation test in your lab, or if you intend to perform, it's quite easy to unload. If you have loaded the red points, if you load it up to 1 point, and if I decide to unload, what I get is a loop. So from B, if I have unloaded, I get to C, and from C, if I decide to load again, what I see is I get a hysteresis loop. So BC is possibly this curve, the lower curve, and CB is the other curve. What I see is a hysteresis loop. This loop again becomes nearly a straight line if I convert this to log scale. And for most practical purposes, I can ignore the hysteresis, meaning I can take this BCCB to be one single line. So this loop which is shown over here, please for the time being, it's considered to be a straight line. If I look at this figure carefully in the next slide, there are a few important terms to understand. So ignore the left hand side figure for the time being. I am on the right hand side figure, the same log scale, the same void ratio. What I see is first curve, then going down to a steeper curve, and from B I have back to C, which was I unloaded it, and then from C I reloaded it. There are a few important things to understand. From B, if I unload, what we see is the unloading is elastic. Why we say elastic? Because I reloaded, it follows the same track. Remember our assumption, this is a straight line, so it follows the same track. Unloading, reloading. The unloading, reloading. So we sometimes call it as unloading, reloading line or URL. This is my unloading, reloading line. What we see is there's a point somewhere here, A, and below this point I also see one line somewhere here. This line has the same slope as the line which is our URL, unloading, reloading line. Obviously, the point over here is the maximum load the soil had seen in its past. So when I took a soil sample, loaded in my laboratory, I probably started from somewhere here. Tuck, 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 tuck. I went up to this point and bang, you see a very steep slope thereafter. What you see is this point was the maximum load your small cake or the sample had seen in its history. In other words, if I remove the soil from say 10 meters below the ground and then take it in my laboratory, remember this soil has already seen 10 meters of its overburden. So if I take in the laboratory and load it, I start loading it up till I reach the level of 10 meters of overburden it has seen in its past. So till that point was somewhere here. This was possibly the 10 meters of overburden, and thereafter the soil has not seen any of these loads. In other words, each and every point over here, if I unload it, so from at this point I have unloaded at B. For example, if I had decided to unload somewhere in between, I could have done that. It's my choice. It's my life. I can do it. So if I had unloaded at this point somewhere here, that point would have been the maximum load the soil would have seen in its history, on its past, and I would have had a different unloading, reloading line. If I use this analogy, this is also my unloading, reloading line. In fact, I can extend this understanding to a point that all the points, which make up this line are, a different unload. I can have different loading, different unloading, reloading at any one of these points. Each point over here, for example, A is shown as over here is the pre-consolidation pressure. So we come across a new term which is pre-consolidation pressure. Pre-consolidation pressure is the maximum load the soil has seen in its past. So this sample, which is from 10 meter depth, has seen a maximum load of say point A over here. Likewise, I can say this line is made up of say millions of pre-consolidation pressure, because I can unload this at any point. Okay, so I can unload this at any point. It will be made up of millions of pre-consolidation pressure. This line is called as the normal compression line, or the virgin compression line, or the K0 line, because it has seen for the load for the first time, so we often call it as virgin compression line or the K0 line. Okay. The next term which is important to understand is, we have is the point B. Remember we said the point B can be anywhere along this line. It's important to note that, if I unload at a point, for example, I have unloaded at this point, brought it to C and reloaded it, okay, to this point, okay, and if I have to move from this unloading reloading curve to the next unloading reloading curve, okay, take an example. I have unloaded at B, brought it to C, and then C I have loaded to B. The next unloading reloading curve will be slightly ahead. Let me see if I have the figure over here. This is plain text. I would like you to read it at home. This is just English what we have said. So, yep, I have a figure over here. Please look at this figure. So from B, I had unloaded to C. C reloaded to B. It's the same thing which you have seen. So from B, if I move to a slightly higher load, a small increment of load, meaning from B, I move to D. What we see is point DD follows the same track. Obviously, this is what we have said. This line is a normal compression line. So once the soil is on normal compression line, each and every point on this line is a new pre-consolidation pressure. So point D, if I unload, that's the new point in the unload, it will have a new URL, a new unloading reloading line. Remember, this is important to understand. I can't jump from one URL to the next URL. If I have to go from this URL to the next URL, I have to first travel from C, go to B. Even if the load is small increment, from B, even if the load is minutely small increment, from B I move to D. In this case, because of the clarity, I have shown that this increment is slightly larger, but it can be small. And from D, I have unloaded it. Okay, so from one URL to the second URL, I have to go to the normal compression line or NCL or the K0 line. It's important to understand. Okay, so that's the small last statement. Stress state cannot move from one URL to another URL without first moving across NCL. This is a law which the soil has to behave. It will not defy this law, never ever. Okay, let's move on to the next slide, please. There are four important interesting definitions or terms, and we'll quickly look at them. They're quite, as engineers, we like to use these terms, whenever we speak with our colleagues, just to show how intelligent we are, how bright we are. So the first term is normally consolidated soil. Okay, that's the, just give me a second. Okay. The first term is normally consolidated soil, and what it means is when the existing effective stress is the maximum the soil has experienced, meaning the existing load is the maximum the soil has experienced, it is normally consolidated soil. So if I want to take this example on the figure which we have just shown on the previous slide, void ratio versus effective stress, can I ask a question? On this line, anyone on this line, which state will be the normally consolidated state? If you look at this figure carefully, this is unloading, reloading. The soil has seen the maximum load A. So A would be normally consolidated. On this URL, soil has seen the maximum load B. So B would be normally consolidated. I can extend this analogy that all the points between A and B and going down to D and so on would be, any stress state on this line would be normally consolidated soil. Okay. The second term is over consolidated. Over consolidated would mean, as obviously if the soil is on URL, any of the URL, the soil has the current stress state less than the stress state, maximum stress state it has seen in its history. So on this URL, if I'm anywhere along this point or on this URL on this point, the maximum stress state is A or B. In other words, the sample or the soil is over consolidated. Okay. The other two terms are over consolidation ratio. That's, we are somewhere here, OCR. OCR is the ratio of the pre-consolidation vertical pressure or the maximum load the soil has seen in its past to the present load. Remember, when we say the maximum load the soil has seen in the past, we speak about effective load, not total load, because only it is the effective load which is important for the soil behavior. The total load will remain constant. So if I apply a total load of, give an example of 100 kPa, allow nature to do its job, allow the sample to compress. So I give it a day, 2 days and come back. So after 2 days, I repeat, the total load equals the effective load because all the excess pore pressures are dissipated. The last interesting term is under consolidated soil. Example of these are your landfills. Landfills, when you dump loose soil, it is yet to compress under its own weight. It has still not compressed under its own weight. So these are the unconsolidated soils. Okay. There's a second term coming up. Next term, please get your paper and pen out. Okay. Remember the same figure, void ratio versus effective stress are the same plot. And we said this line was our K0 line, normal compression line or the VCL line. In this plot, if I look at the change in void ratio versus the change in stress, remember the stress is in log scale, so I would have log, say, sigma V2 minus sigma V1. So if this is V2, this is V1, so log this minus log this. This is this horizontal white line, and vertical white line is the change in void ratio. There is a term which is used and it's called as compression index. Why index? Because this is a dimensionless parameter, and when I say index, it means it's a soil property. It will not change. In other words, this slope of this line, which is shown by compression index CC, is defined as the change in void ratio to the change in effective stress but in log scale. So it's E1 minus E2 divided by log of sigma 2 prime minus log of sigma 1 prime. Remember, I have purposely taken this as 2 first, and in the numerator I have taken 1 first. This is just to avoid this whole thing being negative sign. Obviously, the slope of this line is more than 90 degree, it is negative. In other words, this whole thing should be negative. So I'm just looking at the magnitude. Please, I'm looking at the magnitude. So in order to avoid the negative sign, I have taken a higher void ratio versus the lower void ratios, E1 minus E2, and I have taken a higher load minus the lower load, both in log scale. I know log A minus log B equals to log of A divided by B. So this is the second term I have put over there. Now I use this as index because index means it's a property of soil. In other words, if I take a soil, same soil element, soil sample, and if I remold it, meaning break it into lumps and then recompact it, put it back into shape, this line will not change. The soil has to come back to this line, no matter how I load. So it's a unique line. For a soil, it's a unique line. So no matter I destroy the stress history of the soil, I bring it back, it will always, somehow come back to this line. No matter how I load, it will come back to this line. Okay? So that is why we say it's a property of the soil. And we say index, the other way of saying index because it's dimensionless. Please look at this. Void ratio has no dimension. Log of A divided by B is again dimensionless, no dimension. Okay. I could also find out the slope of this URL. Remember, this is we have just looked at the slope of NCL. I could have done the slope of URL in a similar way. slope of URL would be, let's be called, in some textbooks it's written as CS, that means swelling index, or CR, or recompression index. It just means the same. Swelling index, recompression index. I could have used the same logic to get this value, okay, the slope of this URL. Let's move on to the next slide. If you have any questions, please ask, raise a hand and ask. I suppose today's class would be extended to next lecture. We would not be able to finish off the entire section on theory of consolidation as very much I would have liked to. There are still about 8 more slides left. So if you have any question, please ask. Otherwise, we will continue. What we have noticed is, yep, we have noticed that you're there. Okay. Don't move the mouse. Okay, you do it. Close this. No, close it. I want to close it. I don't know what you're doing. No, you don't need to. I just looked at it. Please close that video. Close it. Thank you. So, any questions, please? No question, right? Okay, we'll continue. There are few. We have about 10 minutes left, and in these 10 minutes, I would like you to make note of few terms. Important terms which are used to deduce settlement. In fact, consolidation settlement is deduced using 4 different equations, and all the 4 equations have, let's call it a mother of all the 4 equations is the first equation, which is on this slide. I would like you to concentrate on the first figure. What it shows is the soil, a complete soil with, of course, voids filled with water, and the surface is loaded. Okay, surface is loaded somewhere here. The total thickness of the soil, let's call it element, or the soil sample, is H, or the thickness of the layer is H, the thickness of the site. So this whole H can be, say, 10 meters. You're just looking at the numbers, okay? But it can also represent your soil sample in your laboratory. So that is a load on the surface. I can represent this whole thing by 2-phase diagram. Remember the 3-phase, 2-phase diagram we did at the earlier part of our lecture series? I hope you have been looking at the notes and doing some problems. Please, we only meet 2 times a week. There is a third hour, at least 1 more hour of the week, which you should be doing some problems. Okay, so I have represented this as a 2-phase diagram, meaning the entire soil is now represented as a solids. The solids are at the bottom of this figure, and the voids which are filled with water are at the top of the figure. Okay, if you recall our earlier analogy, the left hand side is volume. So on the volume, the bottom volume of solids, if I assume it is 1, and you may recall the volume of voids is void ratio. In this case, I have written as E suffix 0. Remember, volume of voids is taken from the definition of void ratio. That's E0 in this case. So what happens if I load the surface? My soil squeezes out, meaning the water will squeeze out. The volume of solids will remain the same, that's 1. Whereas the volume of voids, in this case now the water will be less. E final is less than the E0 because the water has squeezed out. And the change in void ratio is delta E. If I correlate this delta E, in terms of change in height, remember the change in height, if I look at this expression at the bottom of the figure, the change in height over the total thickness H, change in height is now represented as, can I write this as the change in void ratio? Why? The change in height is in 2-dimensional, it's change in height. I can extend this whole figure and to 1 unit which comes out and hits you. That would be the change in volume. So change in height I can write as change in volume, because change in height times the dimensions which comes out and hits you would be change in volume. Again, original height is represented as the total volume. So delta V by V. Can I say change in volume is the change in void ratio? That's delta E. And the original volume was 1 plus E naught. That's the denominator. So change in volume over original volume is delta E over 1 plus E naught. So in other words, change in height or the consolidation settlement equals to H, that is the total thickness times this whole value. This is what has been written over here. The consolidation settlement equals to delta E over 1 plus E naught times H. This is the first, I would say, this is the mother of all the consolidation settlement equations we will see in the next 5 minutes. We'll come to this question. It says just in the last 2 minutes. I think, okay, JNTU teacher will come to your question. Your question in fact is not related to today's class, but we will take up this question just in the last 2 minutes. Please bear with us, okay? I request that, the question should be more relevant to the class, but in this question, I will just come to this question in the last 2 minutes, please. Okay? Let's move on to the next term. We have the first definition of consolidation settlement over here. Okay, that's delta E over 1 plus E naught times H. Remember, please jot this definition down. It's important. If I remember our definition of coefficient of compressibility, remember the few slides earlier, we said AV was the coefficient of compressibility, and it was defined as the change in void ratio over the change in effective stress. This is not in log scale. Remember, this is not in log scale. So I can then replace my change in void ratio in the earlier equation by AV times delta sigma prime. Remember this equation on the previous slide was this fellow over here. Over here, the change in void ratio I can replace by this AV times delta sigma prime. So this gives me a second equation for consolidation settlement. So SC equals to AV divided by 1 plus E naught, okay, times delta sigma prime times H naught. H naught is the original thickness of the layer. So this is the second definition for consolidation settlement, wherein I have now coefficient of compressibility. I will now use a new term, which is AV divided by 1 plus E naught. AV divided by 1 plus E naught is defined as coefficient of volume compressibility. Okay, so AV divided by total volume, initial volume, coefficient of volume compressibility, which is defined as MV. So I can replace this whole thing by MV, okay, to write this equation at the bottommost of this slide. Consolidation settlement equals to MV times delta sigma prime times H naught. This is my third definition. Okay, so this is my third definition or third equation using which I can derive my consolidation settlement. Let's move on to the last one, which is the fourth one. It involves the use of compression index, CC, compression index. Remember, compression index was the slope of this, a slope of NCL or the K0 line, and it was defined as CC equals to change in void ratio divided by log of sigma 2 minus sigma 1 prime. Okay, I can replace the change in void ratio in the first equation. Remember, the mother of all equations. I can replace the change in void ratio by the CC times this whole lot. So it leads to the fourth equation, which is consolidation settlement equals to CC divided by 1 plus E naught. Okay, this is times H naught into log of sigma 2 prime by sigma 1 prime. Okay, Cc times this whole thing is Cc times this whole thing, and I have H naught over 1 plus E naught. Okay. Sigma 2 prime is the higher load, sigma 1 prime is the lower load. Or can I say if sigma 1 prime is the existing load or existing effective load on the soil. Okay, we will look at it where. Then this change is the load coming out from the superstructure, so I have written as delta sigma prime. So in many textbooks, sigma 2 prime is replaced by sigma v prime, that is the existing effective load plus the change in load divided by sigma 1 prime, which is the existing effective load. Okay. This is the last slide. We will pause on this slide and move to the question, but this in a sense means I would like you to go home and look at this slide carefully. What if the existing effective load, sigma V is the existing effective load, is somewhere here, and because of the new construction, the change in effective load is from there to there. That means I reach a new void ratio value of E2. In other words, I have to cross the pre-consolidation pressure. Okay? So I would like you to go home and look at this carefully. It follows a simple logic that I need to find out, use the change in void ratio is E0 minus E2. This should include the change in void ratio because the soil moves along the URL plus the change in void ratio because the soil moves along the K0 line. Okay, please go home and try this. I'm going to move on to this the chat session. The previous question, someone had asked a question. Where is the question? Okay. So view this chat. It says download permission is already there. That's for you. Okay. The question by JNTU A teacher is how external deformation results in settlement. Can you explain it by taking with practical example? JNTU a teacher, I really cannot understand your question very well. It says external deformation results in settlement. Now settlement is something which is manifested or developed, so it exists on an outside. Remember, an external deformation is also outside. I would say both external deformation and settlement are the same meaning. They have the same meaning. So I really do not understand this question, because if the question is related to internal deformation is strain and external deformation is settlement. Okay, so if I have to take a small soil element within the soil mass, and if the soil element squeezes in, it means the soil element undergoes strain. So each and every soil element undergoes strain, which results in overall ground settlement or external settlement. So I really do not understand your question, because to me both external deformation and settlement have the same meaning. Okay, please can you rephrase the question if I'm not very clear? Keep that mouse over there, please. It becomes very confusing for me. Oh, I'll do it. It becomes confusing. Or you just tell me what is to be done. Okay, please. DC, are you teacher? We are with you, please.
Good morning, sir. Good morning, sir. Am I audible, sir?
Yes, you are audible.
Hello?
Good morning.
Sir, my question is regarding the rate of loading. Doesn't it affect this rate of loading? Doesn't affect the nature of consolidation or this compressibility index?
Okay. I'll answer this question by looking at Terzaghi's theory. At the time of Terzaghi's theory, there was a major theory working on in terms of consolidation. This larger theory on consolidation, if you have heard of the term, it's used as Biot's theory of consolidation. In Biot's theory, the loading, meaning the externally applied load, is changing, whereas at the same time consolidation also occurs. Okay, so what you're looking at is a consolidation which occurs at the same time as the load is also applied. Over here, the application of load or the rate of application of load is important. Whereas, Terzaghi simplified this entire thing into a very simple theory, which we normally use in our routine practice, that is the consolidation theory. In this case, it is assumed that the total load you have applied, maybe on the surface or on the soil laboratory or anywhere, the duration of the load you have applied is ignored. So it assumes that you have applied a load, say X, and the consolidation starts afterwards. So it in fact ignores the rate of loading. So your question is very valid or very much applicable if you're looking at loading over a larger duration of period, or loading at the same time as consolidation progresses. In this case, Terzaghi's theory is not valid. You cannot use this theory. You would have to use Biot's theory of consolidation, which I'm afraid is rather complex. And usually, even at master's level, we tend to ignore that. It is only at the research level many of our students work on it.
Thank you, sir.
You're welcome.
Sir, another problem, the presentation is not downloadable. It is, the permission is denied now. So please allow, sir.
Okay, I think my people over here tell me it's downloadable, but let me. Okay, he has a mouse, I have a mouse. What happens in between? Both fight over the mouse. Never mind, he's doing it. He has cancelled download permission and he has redone the download permission. Can you try again and see if it is downloadable?
Yes, sir. Yes, sir. Now it is possible, sir.
Okay. Thank
you, sir.
Thank you. Okay, we have exceeded 5 minutes. So if anyone, any question, if you're still there, any burning question you would like to ask, the question on the chat session is still there. If any question you would like to ask, please either on chat session or anywhere, let me know. Otherwise, thank you. We will continue with this session next time. Thank you. Goodbye.